Welcome to the next Rise of AI virtual chat. My name is Fabian Westerheide. I'm an entrepreneur and investor with a passion for artificial intelligence. And today we talk about quantum machine learning. It's not the easiest topic. It's part of the quantum physics plus the combination of AI. At the end, I will speak with my guest Claudia Pohlink about how we can use quantum computers to use machine learnings and what the impact will be of this combination of two main technologies. So just keep watching, enjoy it. It's a live show as usual, and then I see you next time. Welcome to the next edition of this Rise of AI virtual chat series. Something we started small a couple of months ago during the Corona crisis is now a regular institution. At least twice a month, I'm going live. Each time I have an interesting guest. So as usual, since this is live, feel free to introduce yourself. So you can share your name, where you are, what you do, and your LinkedIn profile. Some already have started. I do the same. Feel free to add everyone. Just add, hey, we met on Rise of AI virtual chat or something like this. This works. We make new context every time. As every episode, I have a different shirt. And I won't tell you what this shirt means. But after the episode or in the chat, you can comment on this. So for a second, have a look on the shirt. And then you can think about what this means. Comment it. Because my wife, she didn't get it. Maybe you get it. Just hint, it's something about the topic today, which is quantum machine learning. And I was skeptical when Claudia Pohlink, our speaker today, and John Michael, you are right. It is Schrödinger's cat. We don't know if she is dead or alive. Wonderful. Then we've solved this. So Claudia suggested the topic of quantum machine learning. And I was like, okay, I know quantum computing and quantum physics, and I know machine learning. How does this work together? And then we discussed this a little bit back and forth, and we figured this out. Okay, this is a pretty good topic. So today we combine the trend of AI and quantum computing. So that also means we will not go that deep into quantum physics. We will try to be more the level to combine those trends. We talk about state of the industries, what hardware can you use, what software can you use, what are use cases, how to deploy it. But we also will give you a first introduction into quantum physics, quantum machines, so you understand a little bit why this is relevant. So now coming to our guest today, which is Claudia. And she described herself as Berliner Urgestein. So she is born and raised in the city of Berlin, but on the other side of the wall. So she is from East Berlin, and she's proud of this. And that's also part of her personality. She's straight talker. She's honest. She is a little bit very casual. And I think this is what East Berlin people have in common. And I like this about them. In the 90s, she did what we call today startups. By then, it was new economy. So after being a student, she went into the new economy. Then in the 2000s, she was in a digital agency, or we call this internet agency by today. Before then, she joined to Yamba. Some people here from Germany maybe still remember Yamba, very annoying ringtones for your cell phone, but it was the second company of the Zamba brothers. And the Zamba brothers are relevant for the European AI ecosystem because they are one of the largest incubators, accelerators, investors, creators of tech companies in this decade. So very relevant. And she there got a network which is very, very important until today. We yesterday talked what kind of people she met, and I know, and it's a huge network. And it's usual. If you start at a small startup, no one knows, and this is going to be big, you grow with the whole market. After this, she left and went to MTV. I think in the 2000s, MTV was still cool. But then MTV struggled. She had her first child, and then later she joined Telecom Labs. Now I would describe Telecom Labs as the German version of Google X. So the German version means less exciting, less ambitious, but still a space where you can be in a large corporation and can do experiments. So they work on AI, they work on blockchain, they work on quantum computing. So since Deutsche Telekom is still a large corporation, an important one, they have the resources, and she's heading this unit, this department in charge there. She's told me she's not an expert. She has a team of experts. Her job is more to identify trends, make a business out of this, manage this, and promote it. I also would say she's an advocate within the company. So this is my brief introduction. Let me bring her online. We have you there.
Hello, everybody. And Fabian, that was such a nice introduction and amazing. Yeah. So I cannot add something because you said everything about me, except one thing. I love numbers. And I also studied data science some years ago. So, but just to let you know, so I'm not just this business expert. I also understand some technologies behind.
And I would say you can't study quantum computing. This didn't exist 20 years ago, 30 years ago, or some people. There are very few people who have done a while ago their PhD. It's the same about AI. I would say today, most people who do AI, they haven't studied AI. It's more the researcher level. How did you go into this field? Like, first, why? And second, how did you train yourself?
So, as you know, my background is more related to business and to marketing. And I realized very early that everything is going in the direction of data. So the business will be data driven. And that's why I decided to go deeper in that area. And I really love the technology and I'm curious about new technologies. And that's why quantum computing is also so interesting. Yeah.
But how do you learn? Do you read papers, go to conferences?
Learning by doing, mostly, yeah. So, and also discuss with the experts and also exchange, of course, on conferences with some more experts outside of the company, because we are not really, DT are not the first mover in terms of quantum computing.
Okay. Before
so for instance, I just to let you know, so I also visited the IBM Quantum Computer in the US last year. So
this was my question. So have you ever seen a quantum computer?
Yes. So that was really, really impressive. Yeah, because
describe it.
Yeah, so this is a huge machine, not that huge as I thought. Yeah, but you can't go into this lab because this is forbidden for visitors, but they can show you the inside of this quantum computer with a prototype. Yeah, then they also try to explain the technology behind, but this is really hard to understand.
And have you ever been on the code level of a computer, like entering a quantum computer, that you see like how it looks in the back end or in the source code or in the infrastructure?
Not myself, but of course my team colleagues. Yeah. So we of course try to code and also to understand this new stuff. But to be very honest, this is very related to machine learning. And if you know Python, then you are on a good way.
Okay. And because it's relevant, the German Große Koalition, the German government has just released a lot of money into the markets, including, I think it's 1 billion for quantum computers.
To be honest.
And it costs
2 billion.
1 billion to buy two?
They want to invest 2 billion in this technology, but the goal is to develop a real quantum computer in Europe or in Germany. So they want to support the hardware, not the software stack or the services around. They just want to develop or support and to motivate to develop this quantum hardware, because at the moment the player in the market are on the US side and also on the Asian side. So Europe is quite behind.
Europe is behind as usual, and it costs so much money to build a quantum computer still.
Pardon me again?
So it's still so expensive to build this, to have this team? Because I have seen a pitch just, as an investor, I see a lot of deal flow, I also see quantum deals, and I've found a team who is able to build desktop size qubit-based quantum computers.
Yeah.
Desktop size.
Yeah, so if we want to talk about hardware, then you should know that there are some differences. There is this classical gate computer from IBM. This is the huge thing, yeah, which you know. May I show you or show some pictures. I would be able to do that if you
Sure,
want.
if you have some slides prepared, you can.
Okay, let me just flip through because this is somewhere here.
Okay, I will make it a focus screen for a couple of seconds so everyone can see it a little bit better. Okay.
So on the right-hand side, you see this IBM cube. Yeah, this is this huge, but this is the inside of this IBM cube. And then on the left-hand side, you see quantum-inspired hardware, for instance, from Fujitsu. This is the digital annealing unit, and this is very funny to see DAO, because in German, this is not the quite abbreviation, yeah, not the quite nice abbreviation, yeah. But it means digital annealing unit, and with this chip, you can simulate quantum computing. Yeah, and then on the left-hand side, you see the technology from D-Wave, which is one of the first players in the market, and this is also a processor or a kind of simulator where you simulate quantum processing.
Okay.
Yeah.
So
and then there's also this processor from Google and so on. But do you see that there are differences between? And you don't need to buy hardware if you want to play around with quantum algorithms. Yeah. So it is. So if you want to know my opinion, then the quantum business will be a cloud business. Yeah.
Okay. First, your opinion is very important. That's why you're here. Before we jump into the hardware, because this is the most practical approach, let's talk a little bit, step back, and let's talk a second for a minute about quantum physics. Because for me, the main question is, like, everyone talks about quantum, why? And then second, why is this relevant for us? Why is this not like all the other physics, just the physics stuff? Why is this real life applicational?
Okay, so I will switch to my slides again because I love this illustration, and this is just this hard, complex problem, or not problem, topic. So that's why it is better to have some slides. Yeah. So that's why.
In the meanwhile, for everyone out there, quantum physics, if you haven't read into it, I recommend to do it. They say there's no one in the world who understood it. I'm currently reading a book where they speak about quantum physics, solving the answer to parallel universes, to human conscience. I think if we solve this will be an explosion of knowledge for humankind. That's why I think it's important to go in this field. It's still so many questions. That's why it's so intellectual, so exciting.
Yeah, and this is also with so many dimensions. And I would like to start here also with this quote, from Richard Feynman, who is a physicist and laureate. And he said, I think I can safely say that nobody understands quantum mechanics. Yeah, this is, by the way, from the New York Times. So, but let's try to understand the technology behind. And here you can see the explanation of the classical computers. And of course, you know a bit, the unit for classical computers, and each bit can store either a 0 or a 1. Yeah. And when it comes to quantum computing, then we talk about qubits. Qubits is special because they can have these two states at the same time.
Which is dead or alive, on or out.
And this means at the same time.
In between.
So,
yes.
And in between, you are right. Yeah. And then there are two more characteristics. These are so-called superposition and entanglement. And the superposition means that there's also an overlay between the two states. And this entanglement is the relation between different qubits. Yeah. So if you have 1 and 2 or 2 qubits, then they are related to each other. Yeah. And this is like a multiplier. Yeah. So you can multiply the computational power. And if you understand superposition and entanglement, then you might understand also that there is a huge power behind, because you can calculate, or you can computate at the same time in all these different states, and you don't need to do it in parallel. And this is the main difference to a classical computer. Yeah.
I know you have a slide for explaining this a little bit better, and we'll come to this. So let me try to rephrase. So if I have a normal computer, it's with transistors, it's like on and off. We have learned this in class or not, that you have machine code, which is 0, 1, 0, 1, or in other orders, and they're expressing states. But with quantum computing or quantums, I can have a state, which can be anything between 0 and 1. It can be 0.85. So it could be, I would say, more precise and more... Again, I'm lost.
Yeah. Yeah. So I recommend also some more webinars about quantum computing. For instance, there's this IBM research lady from, her name is Dr. Talia Gershon. Yeah. She also tried to explain the technology behind. And the thing is, you have to rethink the whole knowledge about computers. Yeah. And this is maybe also the hardest point here when you explain the difference. Yeah, so it's a completely different understanding of computing. Yeah, so
and of physics, by the way. So if you understand quantum physics, it's giving you answers for problems you didn't know they exist.
Yeah,
and it is very philosophical extreme sometimes.
Yeah, so here you can also see the
I like this chart.
Yeah, so it's about CPU, GPUs, and quantum. So that you can see the CPU is working sequential, the GPU in parallel, and then the quantum hardware is working simultaneous. Yeah. So here you can see the opportunities. Yeah. And of course, there are so many challenges already still there. Yeah. So I don't want to hide that there are also challenges and huge challenges. For instance, if you have more than 1 or 2 qubits, so if you double the qubits, the more the relation, because of this entanglement, is getting more fragile. Yeah, so the calculation could be very fragile. Yeah, so just to let you know, yeah, and also the energy consumption. But let's talk about later.
I have the first question I will ask in a second. But first, so CPUs are, if you have a computer, that's a standard computer. It's how you measure mostly, I think, gigahertz or megahertz. This is what went from, it's like, let's say today you buy a dual core, quadro core, or something like this, but it's the normal computer. Then they use GPUs for male neural nets. I think GPUs are coming from the video cards. I know when I played a lot of video games, GPUs very important, and they are really good for neural nets. I think they can't do complicated math, but they can do a lot of math very fast. Yeah, which is good for neural nets. And then we have quantums, which I don't understand, but from your chart, you told me it means there's a bottleneck. So the more data I have, the more complex something is, the less likely I can solve it with GPUs or CPUs, and the only possibility to solve it will be quantum. Before we go into this, one question from Ramesh. He's asking, what is quantum entanglement?
Yeah, so let me put the slides off. So I have to go back to the browser, so then I can see you. To be very honest, I can't explain. So in German, it is Verschränkung. Yeah. So it means that every qubit. So if you have more than 1 qubit, they are connected. So if you do something on 1 qubit, then you can multiply the power with the second one. But there is this, let's call it a cable, something like this. So can you imagine? So there the qubit is not working independently. Yeah. So but they call it Verschränkung, and more I can't explain right now. Sorry.
Just to give food for thought out there, if you measure whatever, how you can measure it, if you measure the quantum physics, they can be very old, like billions of years old, and you measure them. There's also this thing, you only can narrow them if you measure them. Like if you measure them, they exist. If you don't measure them, you don't know if they exist in the state or not. And this is still in my mind. I hope it makes click one day, but smarter people don't get it either.
Okay.
For this question, then we have one. I'm trying to read it. And let's go to the next question, which is, what do you mean by quantizing the data using the present machine learning algorithms?
Did
That's
I
for
say
you.
that? Yeah.
Oh,
I'm not sure if I understood or if I got the question right. But maybe let's
just for Ramesh, this is good. I'm collecting all this because we can go on certain levels up and out with all our talks. So this is good. If we can't answer, that's totally fair and fine. So let's go back to where you wanted to continue.
Yeah. Maybe it will be also the answer for this question. So let's try it. Yeah. So the thing is, because you mentioned the complexity. Yeah. So we also say that Moore's law is ending. What you see on the graph. Yeah. So there sometimes it's not possible to calculate any
Yes, the
numbers
space for
anymore. Yeah.
transistors, I think the space for transistors is narrowed. And if they want to place more transistors on certain layers, they already did this, but then it's a question of heat and cooling. And that's why they have a couple of processors, but at the end, each processor didn't get better. Just for me, when I purchased a computer 15 years ago, it has the same processor size, just only 1 and not 4 or 8.
Yeah. So here is the chance for quantum computing, because the most or let's say calculations which is possible with quantum computing is the optimization stuff. Yeah. So an optimization is also nothing new. An optimization you can also do with machine learning. But here let's just take an example. Yeah. So if you take navigation, yeah, and in the navigation app, for instance, in the city, yeah, and you want to plan your route from A to B. You get this route recommendation and you start to drive. And then let's say due to the high volume of cars, you stuck in
jam.
Yeah, right. And then you see the traffic jam, and then you get a recommendation from your navigation app. Please use this alternative. But all the cars behind you get the same recommendation for this alternative. And then after, let's say, 2 or 5 minutes, the next route is also full of traffic jam. So here comes this holistic approach from quantum computing in the game. Yeah. So that means you would be able to do this calculation in much faster time, so that you are able to calculate different alternative routes to the different cars that they provide this traffic through the whole city. Yeah. So you will have this holistic view on the whole city, and you can also combine this navigation with different variables like air pollution, traffic lights. Yeah, so maybe there's a specific traffic light Schaltung, I don't know, the circuits, I don't know, and also 30 zones in front of schools and so on and so on. So you would be able, with this holistic approach, to provide the traffic through the whole city at a minimum of time.
Why do I need a quantum computer for this? Why don't I do it just with a lot of normal computers? I mean, Google Maps tries to go into this direction.
Because of the Moore's law. Yeah. So it's very hard. So let me give you another example to explain the complexity. So because I really like this example, let me just share the slide again.
So for me, my internal summary is that there are certain problems which are too complex for normal computers to compute. They like encryption. Good example. They can't crack encrypted code.
This is related to the encryption. So let's start with this legend of Fable. Do you know this story?
Yes, I know the if you place one corn of rice there, you double it. And it's called exponential growth. I think
about exponential growth.
Yes.
And you see in the headline the number of the
Right.
grain of rices. Yeah.
Mhm.
And this number you can't really say in English. So I tried it, and this is about, let me just check. I think quintillion. So 18 quintillion. And also when it comes to calculate combinations. So for instance, if you have a table with 10 people at the table, yeah. So what do you guess is the number of combinations? What you can place the different people on this table with 10 people? What would you say?
I think I learned this in school. Stochastic. Is it like 10
Yeah.
times 10 hoch 9?
No, it's not about this 10 hoch 9. It is about faculty.
Oh yes, with this
Fakultät.
Ausrufezeichen. Yes.
Yeah, right. So you have to multiply 1 times 2 times 3 and so on. And if you have 10 people on at the table, then it is 3.6 million opportunities or possibilities.
Wow.
Which is a lot. And when it comes to 20 or 30 combinations, so you can't imagine the number. And this is the reason why this holistic approach is so important, and why the classical computer is at its limit. Yeah, that's the reason, because you can't imagine how this growth is exponential. Yeah, I would say.
But then let's go. So one answer is we need this because Moore's law is limited and current computers can't solve all problems. But since both are so fundamentally different, tell me a little bit how the computing works, or why is quantum this getting along with so much complexity, with so much data?
Let me just check if it's possible. Maybe with let's talk about Peter Shor. Yeah, I will stop the presentation. Peter Shor in 1994.
Okay.
He invented the so it's about prime numbers. Yeah. You know prime numbers?
Yes.
Yeah. And one of the biggest math challenges is the prime factorization, so that you split a number into prime numbers. Yeah. And here we are coming to cryptography. Yeah. So because when you want to encrypt your computer or something else, yeah, it is very cool to use prime numbers. Yeah. But if you would be able to decrypt with quantum computers the whole let's say code, yeah, or the key in seconds, yeah, so then it would be very dangerous for your
I
whole.
mean, we have heard that quantum computers are great for encryption. My theory or my understanding is because it can do so many iterations in parallel, or it just can solve problems fast. I will ask you in a minute how you technically do this, like inject the problem there. But for now, I try. So for I understand. For large data sets, like you said, root optimization, encryption, where I need a lot of tries, or where I have a lot of input data, quantum computers are a good approach, which are solving something normal computers can't do because Moore's law is limited and we don't have really progress there.
Maybe I can also show another slide, which shows also the power. I took the slide from Hartmut Neven, who is the leader of this quantum AI lab at Google. Yeah. So I'm sure you already heard about this quantum supremacy. Yeah.
Yes,
so,
it was like last year in November.
Right.
I heard it.
And they took this specific computational task. And here we can see the differences between this quantum processor from Google and a normal or a classic supercomputer. So you need for the same task 10,000 years when you compare it to a quantum processor in 200 seconds. So here you can see the chances and the opportunities. So don't try to understand the technology behind, just see the results and try to imagine what kind of problems we would be able to solve in the future. If you can save time and also energy, by the way. Yeah.
Okay, so for the people who are just listening in, not everyone is always watching. What we see here is a slide where we see the difference between a quantum processor and a supercomputer, just benchmarking one solving task. And the quantum processor needed 200 seconds to solve it and used electricity in the value of €0.50. While a classical computer would need 10,000 years to solve this, and it would need what, 90 billion euros to, or is it like, let's see,
this is
more?
The energy consumption.
It's the energy consumption. So just saying it would be very long and very expensive. Yeah. So this comes to the point, let's talk about use cases. Like what fields makes it sense, A, to go and say, okay, I'm an engineer or a developer, I'm a company, maybe I will try out quantum computer, and what problems can we solve with this, like already today and in the near future?
So I like this chart.
Okay.
So here you can see, first of all, 3 huge areas, and most of the quantum computing players or the community is talking about these 3, let's call it dimensions. Yeah. So we already talked about cryptography, which is in the middle in the part of quantum secure communications. Then we also have quantum sensing. Sensing is about also a specific kind of measuring, for instance, temperature, yeah, with quantum sensors. But this is not a field where we are in at Deutsche Telekom. So we are dealing with quantum communication and also with quantum computing when it comes to the so-called routing optimization. And if you just imagine the car problem, we also have this in our networks, by the way. Yeah. So these are, let's say, the 3 areas. And then I like this chart as well. This is from Gartner. And here you can see the clusters of use cases, yeah. And then you have this quantum chemistry, because I think there are some industries who are more interested in quantum computing than just a telco, because in the chemistry there are so many or so huge challenges in regards to the complex problems that they are investing very intensively.
I know I read about this. They're using this to rebuild atoms and ions, and then they're rebuilding whole. They reinvent physics, like gravitation and new products and new ways to combine different chemistries to create new materials.
Yes,
highly interesting.
Yeah, and then also about drugs, yeah. So on molecules. So in terms of biology, so they are really interested in to simulate the molecules, and therefore they're using quantum computers. And then you see the magenta circles around computing, which is in details job shop scheduling. Yeah, so the optimization of jobs in industry or in the plant, for instance, route planning, all optimization challenges and so on. Yeah, and of course pattern matching and machine learning. So then you see also this smaller bubble. This is about quantum communication and encryption. Just to give an overview on the use case classes. Yeah. And then I also like this chart because here you see the industries, and of course I will share the slides after that if you want. Here you see the high-tech industry, and they're also interested in the search. So to optimize the search with quantum computers, yeah, which is also cool.
A lot of data.
Yeah. Then traffic simulation, e-charging stations, parking search, of course, autonomous driving, and so on and so forth. Yeah. And then here in the part of the telco industry, this is something really new. So all the telcos are, let's say, not the first movers. We are more the observers right now and try out the first use cases within our industry.
Okay.
Yeah.
So this leads me to a good question which we have here from York. He says, great insights. Could you both share newsletter feeds or podcasts that you stick to keep up with the development? There's so much out on AI, but I'm looking for good sources to track the topic in a digestible manner. So if you want to share your slides, I will forward them to the audience later. And if you also can give me your book recommendations, your blogs, your newsletters, anything which you would say is a source you look for your inspiration. I can enrich this by AI, but if people want something for AI, I already have written about this. But for quantum machines, honestly, I would like to learn more. So just tell us who's your expert, you're the one you're learning from. That would be nice if you can share this with us.
Yeah. So I often talk to the players. So I mean IBM, Rigetti, D-Wave, Fujitsu, so all the different let's say players in this market, and I will show you also an overview of the ecosystem. And they provide us with papers. So it is still a scientific topic, I would say. So most of the insights you will get from papers from the universities. Yeah. So
That's
sometimes
fast.
so sometimes it's really hard to understand all the stuff behind. But this is the most interesting stuff. And then also, of course, Medium, and then also on YouTube you find very interesting talks and webinars about quantum computing, because this topic is really rising. Yeah.
Just give us, let's say, your top 3 papers and videos and that stuff. By the way, I did the same with AI. I started reading papers because there was nothing else, and then it started. Next question, because I will always use questions from the audience preferred over mine. It's from Willie, and he says quantum machine learning will make our algorithms even more of a black box than they already are, won't they? I mean, we can only say if the cat is dead or alive if we open the box. Example, if we carry out a measurement. Interesting. So we had a discussion before. You have been participant there with Berula about explainable AI. How do you see the black box in this terms?
So the interesting fact is, you know how hard it is to explain the AI when it comes to deep learning, and neural networks. But here in that case, the quantum machine learning is coming. So maybe it will be possible to explain AI with quantum computers. So so you can do a competition between machine learning and quantum computing and algorithms on quantum computing to explore both directions. So there is a scientific group, and they are expecting more in terms of deep learning when it comes, or when they apply the deep learning stuff on quantum computers. But therefore you need to transform the models into their language. So that's why I also brought a slide with me about the languages, because this is very similar to this classical computer stuff, because there you see this is a new era of computing, and this is also about a computer stack. This is also about computer languages and so on. But as I said before, if you know Python and if you are able to understand machine learning, then you are in a good position also to understand quantum computers and to apply machine learning to quantum computers.
But then the question again, deep learning is already a black box, which is hard for us. Will make quantum computer machine learning it even more hard to understand, or will it make it easier?
I would say it my opinion. I would say it will be helpful to understand all the stuff behind, which is not really explainable right now.
Okay.
And then
before we go into the ecosystem, one more question from AC. And AC asks,
AC, hi, AC.
She says, on the chart we had a CPU, same location, different time, GPU, different location, same time, and then quantum, same location, same time. She was expecting different location at different time. Not every answer, not every question has to make sense. Like,
Yeah, no,
I'm
thinking about a nice comparison. Yeah, but I would say different times, different places, all mixed together, something like this. Yeah.
Okay, I know.
So and there's another comparison. When you rotate a coin, so you know a coin, and then you have Kopf and Zahl, a number and I don't know the English word for the other side. Yeah, so you have two sides, which is comparable to 1 and 0. And if you rotate this coin, you have the states there at the same time, both states. And this is also a nice explanation for this. You can't say it is a 1 or a 0 because it is
It's interesting.
rotating.
It's also more dynamic, right? I mean, if I rotate a coin, I have both states at the same time, and only if I stop it, I measure it, and then it's stopped. It's not moving anymore.
Yeah, and then also if you have so you can't expect the same result in the second calculation.
Oh yes, that's another weird thing about quantum physics.
And this is also comparable with the coin, because if you rotate the coin, it will never land at the same place. Yeah. So if it comes down.
I will send you the slides in a couple of hours once I have them. I will also send you more book and reading materials. In the slides, you will see how you can start, what is the hardware, what is the state of the AI. In 2 weeks, which is the 25th at 4 p.m., we will talk with Sean Moore. Sean Moore is head of TrueFace, and he's running a company who's doing image recognition, and I call it surveillance technology. Hot topic because everyone is currently pulling out of the market. He's saying, oh, if Google is not doing it, I will do it. So I will talk about him, how AI will be used to do face recognition, video surveillance. He is for it. I'm more skeptical. You will love my shirt, by the way. And I will see you. Sorry that this was a little bit short at the end. We are missing 15 minutes. I will send you the slides. Have a great day, and we see you again. Bye.